Okay, it says it's recording, so yeah, LOL, I'm taking its word for it. So today we're doing a video on chemical shifting. Shouldn't be very long, just kind of like a run through of the basic topics. And what is chemical shifting? And we care most about chemical shifting in regards to how changes in molecules change the chemical shift values of those molecules in spectroscopy. And if you're like, bro, those are a lot of words, then really watch my last video, because it might make more sense to watch that video and then watch this video because of my teaching, but or not. You can just do what you want. So the location of the signal, which is defined relative to the reference compounds, tetramethyl, sorry, my handwriting is acylane. And we're using tetramethylsilane as our reference compound because it has a chemical shift value of 0 in a spectrometer. So we use tetramethylsilane as our reference point for all other chemical shifting values. So for most organic compounds, the signals produced will be between about 0 and 10 ppm. And ppm just stands for parts per million. So if this is our spectrum of our spectrometer, this is chemical shift values, and compounds will give off signals anywhere along this, it was ugly, anywhere along this spectrum. And there are different factors that cause signals to appear in different places and then also appear differently from themselves. So the biggest part about chemical shifting is the idea of shielding, and shielding is very important. So if you understand shielding, that's basically half of spectroscopy, no cap. So shielding happens because the induced magnetic field of the electrons in an alkane, alkene, alkyne counteracts the external magnetic field. And we know that in a sorry, I almost used a bad word, the external magnetic field. And we know that the external magnetic field can be abbreviated as BO, as I like to say. But basically, we have a compound, and even if it's something as simple as C bonded to H, there's there's stuff around it that we're not talking about. But this bond has its own induced magnetic field. And if we apply an external magnetic field to this compound, then the induced magnetic field will automatically try to go against it. So it's kind of like when you planned on cleaning your room, but then your mom tells you to clean your room, and then now all of a sudden you don't feel like cleaning your room because your mom told you to. So these little currents have electrons in them, and they're going against the external magnetic field. And this idea is called shielding. And the shielding is different in different parts of the same molecule, and that's what reveals the structural information of the molecule in spectroscopy. And you're like, bro, that was a lot of words. Okay, so we're just going to go over piece by piece, and then we'll go through shielding, ring currents, electronegativity, lots of big kid stuff. So the first thing that we need to know regarding shielding is that protons in different environments, chemical environments, have different chemical shift values. So my favorite example, which we're going to do, is this alcohol. So I'm going to draw the hydrogens that we have available. And one of the major things to determine how shielded a molecule will be is the proton's vicinity to electronegative molecules or some sort of reference point in the molecule itself. So we know that oxygens have high electronegativity levels compared to carbons. So these electrons that are on this oxygen are going to pull in the electrons on the hydrogens. And even though there aren't very many electrons on hydrogens, an inductive effect is created where this really strong partial negative will pull in the electrons on the hydrogens like this, So all of these hydrogens have electrons and they're being pulled towards this oxygen. And the inductive effect explains that this pull gets weaker and weaker the further away you get from the oxygen. And since the electrons are being pulled off of the hydrogen, there's a proton, an electron, and a hydrogen. Since the electrons are being pulled away, that's leaving the hydrogen naked. It's naked. So I kind of relate this to the idea of peer pressure, where if you are a hydrogen that is closest to the bad influence, then you are more likely to be de-shielded and go do something bad. So that means that in order, this hydrogen would be the most de-shielded because its electron is being super naked, pulled away from it. These hydrogens will be next in line, still going to do bad things, but they're a little hesitant. And then these two hydrogens are like, wait, maybe I should call my mom, maybe I should go home. And these hydrogens are like, bro, what are we talking about? No, I'm not doing that. So that's basically the idea of shielding and de-shielding. And when we put these protons on a chemical shift axis, we know that this is not the exact number value, so don't quote me on this, but we know that this H is the most de-shielded protons, I forgot to mention, I'm sorry, will be on the left side, downfield from TMS. TMS is 0. And they also occur at a higher frequency, and we'll explain why later, probably a different video, but okay. So if this area is more de-shielded than this area is more de-shielded than this area, then that means that this right side of the spectrum is upfield, has a lower frequency, and will be more shielded. So using that logic, we're going to place the electrons that are in our alcohol and put them on this spectrum. So our first hydrogen is going to be purple, and we know that this hydrogen is the most de-shielded out of all of our kinds of hydrogens. So this hydrogen is going to, throw it up right there. And then these two hydrogens are next in line, so they're going to be right there. And this is not accurate representing integration or multiplicity, but we're going to get that in a later video, so don't freak out. Don't give me crap. These hydrogens are next in line, so another signal. And then these hydrogens are next in line, so they're going to be this way. So you can see that as the inductive effect is applied to the molecule, the closer the hydrogens are to the electronegative molecule, the more de-shielded those protons will be, which means that chemical shift is a function of molecular structure. So I'm gonna write that down. CCS is a function, big F, of molecular structure. Okay, so something that we learned in class was that different spectrometers have different megahertz values because they have different electromagnetic fields inside of the instruments themselves. So the reason why we measure the chemical shift values in ppm, parts per million, is because ppm is independent of the instrument. And one thing that we learned was this equation. So chemical shift, this is both for chemical shift. Don't get it confused with partial negative or partial positive. Those are not the same thing. But chemical shift equals the frequency shift from TMS, which is in hertz, divided by the instrument's magnetic field strength in megahertz. So if we were given a value of 7.3 ppm for chemical shift, and we were given that the instrument's megahertz value was 300, then we would be able to solve for the frequency at which that chemical shift value actually happens from TMS relative to TMS. So that's math that you can do by yourself. So we're just going to keep rolling. So now we can correlate structure itself to chemical shift, because I explained how oxygen was electronegative and that caused shielding, de-shielding of the protons, but now we're going to actually explain why that happens. So one of the ways that we can correlate structure to the value of chemical shift is the idea of electronegativity. Electronegativity. Okay, so as electronegativity increases, chemical shifting increases, and this makes sense. So if I have a molecule that looks like this, fluorine is hella electronegative. We knew that already. We knew that from Gen Chem 1, Gen Chem 2. So these electrons around fluorine are hungry for other electrons. So they're going to pull these electrons away from the hydrogen, which leaves their protons naked. If you think about it as naked, it'll stick in your brain, I promise. So these hydrogen protons are now naked, which means that they will resonate at a higher frequency and appear further down fields, de-shielded, compared to TMS. So they would be, on more downfield, more de-shielded. Okay, so even though my numbers are not correct, that's basically the idea. And conversely, as electronegativity decreases, the chemical shifting decreases. So we know that fluorine is the most electronegative atom on the periodic table, but let's say we use something like ammonia. This chemical shift value is 2.2 compared to this CH3F is 4.3. 4.3. So you can see that since nitrogen is less electronegative than fluorine, that means that the nitrogen is not pulling as hard on the electrons of the hydrogen surrounding it in order to make it more de-shielded. Think about it, peer pressure. The stronger the bully, the more likely you are to do something that is bad, and then your mom will yell at you. So this effect of electronegativity increases as you add more electronegative atoms. So if we're talking about the difference between CH3Cl and CH2Cl, CHCl3, then we know that the level of de-shielding will increase as we add more electronegative atoms, because the chlorines that are surrounding this carbon are hella pulling on the electrons of this hydrogen. So this hydrogen is really naked. It's going to do something really bad. So that means that the values that are correlated with this de-shielding makes more sense, because this de-shielding chemical shift is at 7.3, this is at 5.3, and this is at 3.1. And that's only because we added more chlorines to the molecule. Okay, so that's basically electronegativity in a nutshell, but we can do an example to help you learn a little bit. So let me see, what examples do I have? Okay, we're gonna put this in the middle, and we're gonna do some science. So first thing we need to do is determine, are the hydrogens in this molecule in chemically different environments? And my next video will probably better explain the idea of chemically different environments. So right now, just roll with it. And I know that this molecule is not symmetrical because it's not, the molecule is not symmetrical. So I know that the hydrogens are all going to be different. So this will be hydrogen, blue hydrogen. These will be purple, love purple. These will be black. And these will be dark purple. So all of these hydrogens are different, and they're in different chemical environments. And the next video, yes, will explain why they're exactly in chemically different environments. But I know already that this oxygen is very electronegative. So that means that it's going to pull on the electrons of the hydrogens, pull them in, leave their protons naked, and then they would be more de-shielded. So one thing that we need to know, that I actually learned today, is that the chemical shift value will be higher. So chemical shift value will be higher, which means more de-shielded for these protons on the right than these protons on the left. And that's because this carbon is attached to more junk, but this oxygen is only attached to one carbon attached to those hydrogens. So there's a greater pull on this side of the molecule, on these hydrogens, than there are on these hydrogens, because this carbon also has the rest of the molecule to worry about, but this carbon's just straight up vibing. It's got its shit done, and its hydrogens are just going to be stripped naked. This hydrogen will be the most de-shielded. So I'm going to put that on my little spectrum, where the hydrogens that are on the very right side will be the most de-shielded. And then these next hydrogens will go in order of what we expect. So the inductive effect decreases as the hydrogens get further away from the oxygen. So these hydrogens will be next on our list, and they're going to go right here. And then similarly, these will go next, pure pressure, and then dark purple will be our last one. So this is not accurate involving integration and multiplicity. I know, don't yell at me. We haven't learned that yet. So that is the idea of electronegativity involving the concept of electronegativity in spectroscopy. We talked about shielding, we talked about de-shielding, we talked about what exactly chemical shifting is, and we kind of touched on the idea of ring currents, but I'm going to make a different video for that because that is very complicated, and I don't feel like making this video hella long. So that's what we learned. I hope this was helpful, and if you have any questions, then just let me know. But also know that chemical shifting is easier to understand as you learn more content. So after we get into integration and ring currents and multiplicity, I feel like shielding and de-shielding will make a lot more sense. So don't freak out if this is scary and you're like, bro, Sophia, what the hell are you talking about? Because it gets easier, pinky promise. So check out my next videos, like and subscribe, LOL, and have a good day.